Data flow computers. Data flow computers are based on the concept of data driven computation, which is drastically different from the operation of conventional von Neumann machine. The fundamental difference is that instruction execution in a conventional computer is under program flow control, whereas in data flow computer is driven by data availability. However, studies have revealed a number of inefficiencies in data flow computing. They are the data flow model incurs more overhead during an instruction cycle compared with its control flow counterpart. The detection of enabled instruction and the construction of results token generally will result in poor performance for applications with low degrees of parallelism. And the execution of an instruction involves consuming tokens on the input args and generating result tokens at the output arg, which involves communication of tokens among instructions. The data driven concept means asynchrony, which means that many instructions can be executed simultaneously and asynchronously. A higher degree of implicit parallelism is expected in data flow computer. Because there is no use of shared memory cells in data flow computers, and data flow programs are free from side effects. Next, data flow principles. The data flow model deals only with values and not with names of value containers that are addresses. This concept is also fundamental to purely functional or applicative languages, and hence these languages have no built-in notion of global updatable memory. An operator in these languages produces a value which is used by other operator. The data flow model has nothing like an instruction counter. An instruction is enabled if and only if all the required input values have been computed. Enabled instruction consume input values, execute and produce a set of output values which are then sent to other instructions that need these values. An instruction in data flow does not introduce sequencing constraints other than the ones imposed by data dependencies in the algorithm. Thus, it is possible to expose all of the parallelism in data flow program. Next, features of data flow computers. Intermediate or final results are passed directly as data token between instructions. There is no concept of shared data storage as embodied the traditional notation of variable. Program sequencing is constrained only by data dependencies among instructions. Next, data flow graphs. Data flow graphs can be viewed as the machine language for data flow computers. A data flow graph is a director graph whose nodes correspond to operators and arcs are pointers for forwarding data tokens. The graph demonstrates sequencing constraints among instructions. In data flow computer, the machine level program is represented by data flow graphs. In a data flow computer, a program is represented by a linear instruction sequence but by data flow graph. Moreover, no single thread of control moves from instruction to instruction demanding data, operation on it and producing new data. Rather, data flows to instruction causing evaluation to occur as soon as all operands are available. Instructions are known as nodes, and instead of data items, one talks of tokens. A producing node is connected to a consuming node by an arc, and the point where an arc enters a node is called an input port. The execution of an instruction is called the firing of a node. This can only occur if the node is enabled, which is determined by the enabling rule. Enabling rule states that a node is enabled only when each input port contains a token. Data is sent along the arcs of data flow graph in the form of tokens, which are created by computational nodes and placed on output arcs. They are removed from the arcs when they are accessed as input by other computational nodes. Concurrent execution is a natural result of the fact that many tokens can be on the data flow graph at any time. The only constraint on evaluation order is the presence of tokens on arcs in the graph. The figure here illustrates an example of data flow graph for evaluation of the expression h square minus 2 into h plus 3. Here, nodes represent the operation to be performed. The fan out of an arc from a node, such as phantom node h, denotes the conceptual replication of tokens leaving that node. A node marked with a constant value is assumed to regenerate that value as often as it is needed by nodes to which it is in input. When value of h is available, it is provided to calculate h square and 2 into h. The following subtraction operation will not be carried out until these values are available. As soon as h square and 2h values are computed, subtraction operation will be carried out, which in turn will provide input to next addition operation. Next, data flow architecture. Depending on the way of handling tokens, there are two kinds of architecture, that is static model and dynamic model. The static approach allows at most one instance of a node to be enabled for firing, that is, a data flow actor can be executed only when all of its input tokens are available and no tokens exist on any of its output arcs. On the other hand, a dynamic approach permits simultaneous activation of several instances of a node during the runtime by viewing arcs as buffer containing multiple data items. Static data flow architecture. This is the architecture for static data flow. In a static data flow machine, data tokens are assumed to move along the arcs of the data flow program graph to the operator nodes. The nodal operation gets executed when all its operand data are present at the input arcs. Only one token is allowed to exist on any area at any given time. Otherwise, the successive sets of tokens cannot be distinguished. This architecture is totally considered static because tokens are not labeled and control token must be used to acknowledge the proper timing in transferring data tokens from node to node. Next, dynamic data flow architecture. A dynamic data flow machine uses tagged tokens so that more than one token can exist in an arc. The tagging is achieved by attaching a label with each token, which uniquely identifies the context of the particular token. This dynamically tagged data flow model suggests that maximum parallelism can be exploited from a program graph. If the graph is cycled, the tagging allows dynamically unfolding of the iterative computations. The static data flow model has a simplified inherent mechanism to detect element nodes, but the model limits the performance because iterations are executed one at a time. The dynamic data flow allows greater exploitation of parallelism. However, this advantage comes at the expense of overhead in terms of the generation of tags, larger data tokens, and complexity of the matching tokens. Next, VLSI computation. Highly parallel computing structures promises to be a major application area for the million transfer chips that will be possible in just a few years. Such computing systems have structural properties that are suitable for VLSI implementation. This architectural style immediately reduces the design problem by similar orders of magnitude. We begin with a characterization of the systolic architecture. Simplicity and regularity of VLSI computation. Cost effectiveness has always been a major concern in designing special purpose VLSI systems. Their cost must be low to justify their limited applicability. The cost can be reduced by the use of appropriate architecture. If a structure can truly be decomposed into a few types of building blocks, the cost can be reduced. This is especially true for VLSI design, where a single chip comprises hundreds of thousands of identical components. To cope with the complexity, simple and regular design are essential. Therefore, VLSI systems are based on simple regular layout. Concurrency and communication. The degree of concurrency in a VLSI computing structure is largely determined by the underlying algorithm. Massive parallelism can be achieved if the algorithm is designed to introduce high degrees of pipelining and multiprocessing. When a large number of processing elements work simultaneously, coordination and communication become significant, especially with VLSI technology where routing costs dominate the power, time and area required to implement a computation. The issue here is to design algorithms that support high degree of concurrency and in the meantime to employ only simple regular communication and control to allow efficient implementation. Computation intensive. VLSI processing structures are suitable for implementing compute bound algorithm rather than input outbound computations. In a computer bound algorithm, the number of computing operations is larger than the total number of input and output elements. Otherwise, the problem is input output bound. For example, the matrix multiplication algorithm represents a compute bound task which is O and 3 multiply add steps but only O and 2 IO elements. On the other hand, adding two matrices is IO bound since there are n square adds and 3n square IO operation for the two input matrices and one output matrix. The higher bound problems are not suitable for VLSI because VLSI packaging must be constrained with limited IO pins. A VLSI device must balance its computation with the IO bandwidth. Knowing the IO imposed performance limit helps prevent overkill in the design of special purpose VLSI device. Thank you.